So water is cool. Water is an acid and a base. It's amphoteric. We talked about that we talked about that concept. We did talk about the water also, but whatever. It's amphoteric. It can act either as an acid or a base. And in fact, it sometimes does that a little bit with itself. Really. It self-ionizes. And you might think, well, why would it do that? So we've got two water molecules, and why would one water molecule give a proton to the other when they're the same? Well, they don't do it very much, just a little tiny bit. So this is an equilibrium, and the equilibrium lies very strongly to this side. But one of the water molecules acts as an acid and donates a proton to the other one, and then we end up with hydronium and hydroxide ions. Okay, and that happens to a very small extent.
But that doesn't change the pH, does it?
We'll get to that. So it happens to a very small extent. Now, we have the advantage of already having done Chapter 15. In Chapter 15, we learned what to do and how to calculate equilibrium constants, right? So here we have 2H2O liquid in equilibrium with hydronium ion. Well, it's kind of silly to say it's aqueous, so let's just leave that out for now. I mean, it is, but whatever. So the equilibrium constant for this would be the concentrations of the products divided by the concentrations of the reactants, and everything raised to the power of their coefficients. But the liquid water doesn't change concentration. Liquids and solids are left out. And so the equilibrium expression for this, what am I doing? The equilibrium expression is this guy right here. KW. KW means it's the equilibrium constant for water. So it's the hydronium ion concentration times the hydroxide ion concentration. And that constant is 10 to the minus 14. 1 times 10 to the minus 14. So does a lot of the water ionize or very little? We have a small equilibrium constant. Very little ionizes. Very little. And we can take this and solve for the concentration of the hydroxide ion and the hydronium ion, and we find that the concentration of each of these, this is this guy up here, I need to revise this slide. The concentration of each is 1 times 10 to the minus 7th moles per liter. Very, very small. So in a neutral solution, the concentration of hydronium equals the concentration of hydroxide. Because we haven't added any acids or bases, and the only hydronium and hydroxide ion ions present came from water. And if you get one, you get the other. So in a neutral solution, those are equal. And this is at 25 degrees Celsius. There are some slight temperature dependencies. We're not going to worry about that. So neutral solution, we just talked about that. An acidic solution has more acid. Acids donate protons, so you're going to have more hydronium ion in an acidic solution. So then the hydronium ion concentration is larger than in that neutral situation, and the hydroxide ion concentration is smaller. Because if one goes up, what happens? See these? Yeah, whatever. Okay, 2H2O in equilibrium with the H3O plus the OH minus. If we increase the H3O plus concentration by adding an acid, what does that do to the equilibrium? It shifts it to the reactants, right? So if this reaction goes this way, what does it do to the hydroxide ion concentration? That must go down, right? Because in order for it to go that way, some of this and some of that are going to react and form water. So if the one goes up, the other goes down. So it's like like a piece of rope over a bar, and one end goes up, the other end goes down. You can't have both go up or both go down at the same time. In a basic solution, if you add base, then the opposite is true. The hydronium ion concentration goes down and the hydroxide ion concentration goes up. But what is true in all aqueous solutions is this equilibrium expression. And so from this expression, we can see that if this hydronium ion concentration were to increase, then the hydroxide ion concentration would have to go down for this expression to remain true. Because if one goes up, the other has to go down.
So in a weak acid that has like 3 ionizable hydrogens but doesn't ionize all the way, if you heat that up, does that cause it to ionize more?
I think it would. The temperature definitely would affect how it ionizes.
How many hydrogen atoms come off?
It could affect the position of the equilibrium.
Mm-hmm. And so it would make it more acidic then for those?
Probably. Don't quote me on that. So here's a graph that's showing the interrelationship or interdependence of hydroxide ion and hydronium ion concentration. So if we go to an acidic solution, the hydronium ion concentration increases, then the hydroxide ion concentration must decrease, and vice versa. So we can do calculations. There's another typo. Calculate the hydronium ion concentration in each solution and determine whether the solution is acidic, basic, or neutral. I'm just going to do one of these because we are running out of time. So what you need to know is Kw equals hydronium ion concentration times hydroxide ion concentration, which equals 1 times 10 to the minus 14. So we are given the hydroxide ion concentration, we need to calculate the hydronium ion concentration. Rearrange the equation and then put the number in. So we want to divide both sides by hydroxide ion concentration. So the hydronium ion concentration will equal 1.0 times 10 to the minus 14 divided by the hydroxide ion concentration that they gave us. And here's yet another example of needing to know how to do scientific notation on your calculator, because you can't put in 10 to the minus 14 as a decimal number. It doesn't fit. Not any one that you can probably put in your pocket. So I'm coming up with 6.7 times 10 to the minus 13. And the concentration is always in moles per liter. Anybody else get that? Thank you. Okay, so that's the first question. What's the concentration of the hydronium ion? The second question is acidic, basic, or neutral? In neutral solution, they're each 10 to the minus 7. So you can think of it, well, hydronium ion concentration, this is less than 10 to the minus 7, so it must be a basic solution. Or you can look at the relative. So this one's 10 to the minus 2, and this one is 10 to the minus 13, which is bigger? The 10 to the minus 2. So there's more hydroxide. If there's more hydroxide, it's a basic solution.